In this section, we'll be looking at mathematical models of mechanical systems. In this part, we'll be mainly looking at the basics of translational mechanical system. What do you mean by a translational mechanical system, and what are the elements that are in the translational mechanical systems? Although there are several physical systems around us, we'll be concentrating on mechanical systems in this section. Our aim is to build a mathematical model of a mechanical system so that we can predict its behavior when a particular input is given, and also to know what kind of input should be given to get a desired output. Now, why we go for a mathematical model? Because it is expensive to actually test out on a physical system, and if the design is wrong, you can end up wasting a lot of money. So instead of that, if we develop a mathematical model, we can test out various inputs until we get the desired output, and then decide on how to build that mechanical system. Now, mechanical systems can be divided broadly into two types: one that moves along a straight line and other which rotates. Now, translational mechanical systems are those mechanical systems that move along the straight line, whereas rotational mechanical systems are those which rotate. You're first going to deal with translational mechanical systems. Our aim while trying to create a mathematical model for a translational mechanical system is to find out what happens when we try to move a physical body through a linear path. What are the factors that determine how quickly that body will move? How much distance will it cover when we apply a force? Now let's look at an example to understand this better. Let's consider a body being placed and we are applying a force onto it such that it moves through a displacement of x. Now, what are the factors that influence this movement? Now, when we apply a force, what are the opposing forces that are offered by this body? First opposition is from its mass itself. When the heavier the body, the larger the force that you need to apply. So, for example, it takes a larger force if the ground, even if the ground is frictionless, it takes a larger force to push a boulder of rock than to push a book. So mass has a considerable effect on how much force we need and how much the body will move once we apply a force. So mass is one of the factors. Now, second one is its elasticity. Now, why elasticity? The concept may be slightly difficult to understand how elasticity affects the movement. Now, here let's consider this as a block of maybe a rock, but instead of that, what I'm going to take is a block of sponge. If I take a block of sponge and if I apply a force, what will happen? It will not move as it would have moved the block of rock. What to do is it would budge, and only a small force will actually end up in pushing the block of sponge. So it is due to the elasticity. What happens? The whole of the force that we applied didn't actually get translated into moving the body. Some of it was absorbed by the body due to its elasticity, which means that elasticity of the body also affects how much the body will move when we apply a force. Now, third factor is the friction between the body and the ground. How much friction the body will offer when we try to move it. Now, rougher the surface of the body, larger the friction, and lesser the distance it will move. Now, if you take any body which we try to move, all these factors come into play to certain degree. If you take a sponge, the elasticity will be highly evident, whereas if you take a block of rock, it has an elasticity, but to a very small extent that we can hardly notice it. So any physical body which we try to move offers opposition in these three factors. So to see that when we apply a force to a body which is free to move, three factors affect the output. How heavy the body was, how elastic the body was. Now instead of sponge, we can actually imagine walking on sand. It is much more difficult to walk on sand rather than walking on ground, because the ground actually helps us to push ourselves, whereas the sand, due to its less rigid surface, budges under our weight, and more force we need to push ourselves, and that is why it is much more difficult to walk on sand when compared to walking on a hard ground. And third factor is how much friction the body offered on the floor. Thus, when it was needed to develop a mathematical model for a translational mechanical system, it was understood that any translational mechanical system can be represented by using three simple elements which represented these three factors. The three elements were mass, spring, and dashpot. Now let's look how these are represented. So mass is represented as follows. So you have force being applied. This is the force. So this is how you represent mass as an element. So this is the reference. This part is the reference that we take. So this is how you represent, you account for the mass of the body. So if a body has a particular mass, then while trying to represent it in a mathematical model or in a diagrammatic manner, we draw like this. This is an ideal mass element. Now next is we are going to look at ideal spring. For ideal spring, what we do is we take there are two ways of representing ideal spring. One is being connected to a reference. So this is one way of representing ideal spring, and you use capital letter K to represent an ideal spring, and you again apply a force, and see that when we apply a force, it will compress itself, just like how a sponge would compress itself when we apply a force. So this is an ideal spring with one end fixed to the reference, but there can be situations where you have spring being connected to two different moving parts. So for that we use this kind of representation where there is two displacements, that is there is x1 and x2. This is x1, this is x2, and we apply a force F. Now we use a dash part to represent the friction that gets offered by the body. Okay. Now to represent a dashpot is basically represented by a piston moving inside a cylinder which is filled with viscous liquid. You know that if the liquid is viscous and if we try to move through that, it will be very difficult. So it offers a friction. So this is how you represent a dashpot. Now again, just like spring, it has two ways. One is it is fixed with one end fixed to the reference, whereas the other way of representing is it has displacement at both ends. So this is a dashpot with one end fixed to the reference when you apply a force, and this shows a dashpot with displacement at both ends. This is x1, this is x2 when you apply a force. So we use these three elements to account for the opposing forces offered by the mass of the body, elasticity of the body, as well as the friction. So mass, which is accounted for the weight of the body, spring, which accounted for the elasticity of the body, and dashpot, which accounted for the friction that is offered by the body on the floor. Now, as I said earlier, a dashpot is a piston moving inside a cylinder filled with viscous fluid. Thus, when we apply a force to a translational mechanical system, it is opposed by these three factors: the opposing forces due to mass, elasticity, and friction. Now, any force acting on a physical body obeys Newton's second law of motion, F is equal to ma, and thus for a translational mechanical system, sum of applied forces is equal to the sum of opposing forces on the body, and it is by using this condition we try to develop a mathematical model for a translational system.